Hi, today we will continue our discussion about the ingredients of concrete. In summary, we have the cement, the aggregates, water, and admixture. Yesterday, we discussed the cement. Today, we will continue discussing about the aggregates. Aggregates occupies about 75% of the total volume of concrete. It affects strength, stiffness, and durability of concrete. Aggregates is less expensive than cement, so we can use the largest percentage of aggregates in a concrete mix. Also, aggregates should be packed and cemented as densely as possible for maximum strength, durability, and best economy. To classify the fine and coarse aggregates, because normally when we say aggregates, it should be a combination of coarse and fine. But how do we know, or how do we distinguish if it is fine and coarse aggregate? We can use different classification system, but here we have the unified soil classification system. In general, we can say it's either silt and clay, sand, gravel, cobbles, and boulders. We will concentrate ourselves on sand and gravel. Sand can be divided into fine, medium, and coarse sand. Also, for the gravel, we have the fine and coarse gravel. So, as you can see at the bottom, I separated this one, the yellow and the green color, so that this will comprise the fine aggregate. The yellow one as the fine aggregate, and the green color as the coarse aggregate. So, as you will notice, for sieve number 4, that's 4.75 millimeter down to sieve number 40, that is 0.425 millimeter. We can consider it as a fine aggregate. For the coarse aggregate or the gravel, it should be from 4.75 millimeter up to 19 millimeter. That's actually around 3/4 of an inch. And you will see that would be the usual maximum nominal diameter of aggregates. The code actually have a compliance requirements for aggregates. We have ESTM C33, the specifications for normal weight aggregates. You have to use this specification in order to classify the normal weight aggregates. Also, we have ESTM C330. This is the specifications for lightweight aggregates. Note that ACI 31826.4.1.2.1b aggregates not conforming to ESTM C33 and ESTM C330 are permitted if they have been shown by tests or actual service to produce concrete of adequate strength and durability and are approved by the building official. Also, for the nominal maximum size of coarse aggregate, the code NECP or ECI permits that it should not exceed the less of the following. We have three options. First, 1/5 the narrowest dimension between sides of forms, or 1/3 the depth of slabs, and 3/4 the minimum specified clear spacing between individual reinforcing bars or wires, bundles of bars, pre-stress reinforcement, individual tendons, bundled tendons, or ducts. To visualize that one, we need an example. So I have drawn several pictures here. As you can see, we have the first diagram, the RC section, with the height H and width P. I specifically draw side forms so that you will see the actual dimension. Here it says the first criteria is that it should be 1/5 of the narrowest dimension between sides of forms. Normally for beams, the width B is smaller or narrower than the height H. So in this case, you can try looking for B over 5 or H over 5. So if we have a 400 or 250 millimeter by 400 millimeter section, so the 250 millimeter is the less dimension divided by 5, so that would be 50 millimeter. Also for the second diagram, you will see an RC section with reinforcements. The code actually specifies a minimum spacing between rebars to be 25 millimeter. So if you use that minimum, the other criteria for the nominal maximum size of aggregate should be 3/4 of bar spacing. So 3/4 of minimum bar spacing, which is 25 mm, that should be 18.75 millimeter. Or 3/4 of an ends, because 25 millimeter is approximately one end, so that would be 0.75 of an ends. Going back, 3/4 of 25 mm is, or 25.4 actually, if you have to really get the exact conversion. It should be 18.75, and we normally approximate it to 19 millimeters. So that's the one that I am telling you earlier. Normally, that would be the maximum size of the aggregate. Also, for the RC slab, we have the thickness of the slab edge, and it should not be greater than 1/3 of edge. Here is an example. Beam dimensions: B is 300 millimeter, edge 500 millimeter, with the maximum spacing of bars 25 millimeter, and the slab thickness which is usually 100 millimeter. So the nominal maximum size of aggregate should satisfy, or we should check all the three criteria and look for the smallest value. So here, first, it should be the minimum of the three criteria above. So 1/5 of the narrowest, that is B. So 300 over 5 is 60 millimeter. The other criteria is that 75% of the bar spacing, we have 25 times 0.75, so it's 18.75 millimeter. And H, or the thickness of the slab, is 100 divided by 3, that's 33.33 millimeter. So here, the minimum value of the three criteria is 18.75 millimeter, or that's 3/4 of an inch. So remember, in reinforced concrete, we normally use the maximum value of 3/4 of an inch. And of course, you can use higher than that if your bar spacing is not 25. Try to design a section where the bar spacing should be greater than 25, maybe around 40 millimeter or 50 millimeter, so that in that way you can increase the nominal maximum size of aggregate. Like for example, if the spacing is around 40 millimeters, so 3/4 of 40 is around 30 millimeters. So considering the three criteria, still 30 millimeter will suffice. So in that way, the maximum nominal size of the aggregate should be 30 millimeter, meaning you can use more than 1 inch diameter of the aggregate. That's how we do it. Because if you use larger than that, what will happen? The aggregate will not go through the section because it will clog up above the reinforcement. Aside from the aggregates, we have the other ingredient, which is water. There should also be a compliance requirement for water according to ECI. Water, or the mixing water, shall conform to ESTM C1602. Also, the mixing water, including that portion of mixing water contributed in the form of pre-moisture on aggregates, shall not contain deleterious amounts of chloride ion, because this is not good for the concrete mix. This is especially when used to pre-stressed concrete. For concrete that will contain aluminum embedments, or for concrete cast against stay-in-place galvanized steel forms. Aside from water, we have the admixture. This is normally not part of the ingredients, but since cement or concrete mix is actually a high-tech material, for it to be high-tech, we need to use admixtures so that we can change the basic properties of the concrete mix. Normally, the admixtures are either mineral or chemical admixtures, which are often added to the concrete mix immediately before or during the mixing. Take note that admixtures for concrete are like a beauty aids for people. So, mura siya pagwapa. Also, admixtures are used to modify the properties of the concrete to make it better serve its intended use or for better economy. For the mineral admixtures, we have the fly ash. Of course, you have to use the specification ESTM C618 for the fly ash. This is a byproduct from the combustion of coal in power plant. Also, we have the cement slag. Use ESTM C989 for the specification of this. This is a byproduct of iron production. This byproduct is first granulated and then ground to achieve particle sizes similar to those of cement. And also we have the silica fume. Silica fume is solid microsilica material collected from the fumes of electric furnaces that produce ferrosilicon or silicon metal. Aside from the mineral admixture, we also have the chemical admixtures. We normally use air entraining admixtures, which forms a minute bubbles that is very small, less than 1 millimeter. Also, we have the accelerating admixtures. If you want to accelerate the setting of your concrete mix, you have to use this one. Normally, we use calcium chloride for this particular admixture. Also, normally, adding more water is not really good for the concrete mix. So, actually, it's much better if you use a smaller amount of water. So in that way, if we have to use a smaller amount of water, the workability of the mix will be affected. In order that the workability will still be good, we can use what we call the water reducing and set controlling admixtures. There are several types of it. Type A, water reducing admixtures. Type B, retarding admixtures. Type C, accelerating admixtures. Type D, water reducing and retarding admixtures. Type E, water reducing and accelerating admixtures. Type F, the water reducing high range admixtures. We call it normally the super plasticizer. Also for the type G, water reducing high range and retarding admixtures. Take note, if you have to reduce your water, again, the workability will be affected. So in order that it can be still workable, you need to add water reducing, or we call it the super plasticizer, the high range water reducer. Also, we have the medium range water reducer. Also note that waterproofing material is a type of soap or petroleum products, perhaps asphalt emulsions. You can also add that one in your concrete mix. Here is the effect of the super plasticizer versus the water reduction. This is taken from the Sika group. So depending on the dosage of the super plasticizer according to the percent of cement mass. So for example, for one bag of cement, that's 40 kilograms. If you say 1% of the 40 kilograms, then that would be around zero point 0.4 of the mass. So you can look at these values, like for example, if you have a super plasticizer of the dosage 1.6, your water reduction should be around 40%. Or you can look at the other spectrum. If there will be no super plasticizer that is zero, then there will be, of course, no water reduction. But here, the average is around 5. But as you add super plasticizer, that's zero point 0.2, the water reduction will increase. That's around 0.6%. And if it is zero point 0.4, that's around zero point 0.8. The mean value, zero point 0.6, the mean value is around 12 or 12.5% water reduction. So as you increase the dosage of the super plasticizer, you will see that you will also increase the water reduction. That's the effect of the super plasticizer. Also, there is a compliance requirements for the admixtures. ECI 31826.4.1.4.1 says that admixtures shall conform to the following: water reduction and setting time modification. You can use ESTM C494. Producing flowing concrete, you can use ESTM. Producing flowing concrete, you can use ESTM C1017. Air entrainment, you can use ESTM C260. And inhibiting chloride-induced corrosion, you can use ESTM C1582. Also, admixtures that do not conform to the specifications in the above criteria shall be subject to prior review by the licensed design professional. Also, calcium chloride or admixtures containing chloride from sources other than impurities in admixture ingredients shall not be used in pre-stressed concrete, in concrete containing embedded aluminum, or in concrete cast against stay-in-place galvanized steel forms. Also, admixtures used in concrete containing expansive cements conforming to ESTM C845M shall be compatible with the cement and produce no deleterious effects. These are all the ingredients in a concrete mix. Again, we have the Portland cement, the aggregates. It can be a fine and coarse aggregate, water, and lastly, the admixtures. It's just a way of playing with the quantities of these four ingredients so that you will get the desired property of your concrete. That's all for today. Thank you for listening.